Welcome to Satoshi and Solana, the show where we break down blockchain and crypto concepts in a fun, easy-to-understand way. So today we are doing a really deep dive into, well, what's arguably the most important technology paper of this century.
It has to be.
Satoshi Nakamoto's 2008 white paper, Bitcoin, a peer-to-peer electronic cash system.
9 pages that basically changed the world.
Exactly. Our mission here is to figure out how this dense little document laid the groundwork for, a whole new financial world. What was the core problem it solved, and why were the solutions so revolutionary?
Well, if you look at the very first paragraph, it just jumps right into it. The whole project is about one thing: getting rid of trust.
Trust in what exactly?
In institutions. For centuries, all of commerce has relied on financial institutions, banks, credit card companies, you name it, to act as trusted third parties. They sit in the middle of every single exchange.
And I think most of us just accept that as, the cost of doing business is just how things work.
But the paper argues that this reliance on trust, it has all these hidden costs, these huge weaknesses.
Okay, like what?
For one, the cost of mediation itself. It makes tiny transactions basically impossible. You want to send someone a few cents for an article you like.
The fee would be more than the payment.
Exactly. But the bigger issue is that transactions aren't actually final.
Wait, what do you mean they aren't final? If I buy something, it feels pretty final to me.
It feels final, yeah. But the bank or the credit card company, they always have the power to reverse it. They can handle disputes, issue chargebacks. They can literally roll back history.
Ah, okay. I'm starting to see it. So that power of reversal, that's the vulnerability. For merchants, they have to constantly worry about fraud, about someone trying to claw back a payment.
Precisely. Fraud is just an accepted, unavoidable cost of doing business because the system is literally designed around reversing things.
So the paper's goal was to build a system where two people could transact directly with each other.
No trusted third party needed.
And it replaces that trust with what?
Cryptographic proof. Math. Something much, much harder to argue with. The whole point is to have finality that's secured by math, not by a corporate policy.
Okay, so let's start there. Peer-to-peer electronic cash. Payments going straight from my computer to yours. But as soon as you take the bank out, you hit this massive wall.
The double spending problem.
The double spending problem.
It's the whole challenge with digital money, right? A digital signature is great for proving I own something. Only I can spend my coin. But if a coin is just data.
What stops you from just copying that data and spending it over and over again?
Exactly. It's like photocopying a $20 bill. If you could do that, the currency would be worthless in an instant.
So what was the old solution to this?
The old solution was just to, bring back a central authority, a mint that would check a big central database for every single transaction to make sure the coin hadn't already been spent.
And now you're right back where you started.
You're right back at square one. You've just traded a bank for a mint. You still have that single point of failure.
So the Bitcoin solution had to be different.
Radically different. The idea is brilliantly simple in theory. All transactions have to be publicly announced to everyone.
Okay.
And then all the participants have to agree on a single shared chronological history of when each transaction was received. We need to prove which one came first.
How do you do that without a central clock?
The paper's big innovation, a peer-to-peer distributed timestamp server.
All right, let's get into the nuts and bolts of that. How does the paper define a coin? It's not a file, is it?
No, not at all. It's defined as a chain of digital signatures.
A chain of signatures. Okay, what does that mean?
So if I own a coin and I want to send it to you, I take two things: the hash of the transaction where I first received it and your public key.
Right.
I digitally sign both of those together, and that signature now becomes the proof of transfer that you can use for the next transaction.
So you're literally signing over the coin and linking it to its entire past. It's all verifiable.
Exactly. Anyone can look at that chain of signatures and verify the ownership all the way back to when the coin was first created. But again, that alone doesn't stop me from signing 2 different transfers at the same time.
You still need that chronological order.
We still need the stamp.
And that brings us to the ledger itself, right? The blockchain. The system puts transactions into blocks.
Correct. The goal is to get a verifiable, unchangeable order for these blocks. The system starts with a timestamp server. It takes a group of transactions, a block, and creates a hash of it.
A sort of digital fingerprint.
A fingerprint that proves those contents existed at that moment. But here's the crucial part. When the next block is created, Its hash includes the hash of the previous block.
And that's why it's a chain.
That's the chain. Every new block is mathematically tied to the one before it.
So if I try to go back and change something in an old block,
The hash of that block instantly changes, which then breaks the hash in the next block, which breaks the one after that, and so on. The whole chain falls apart. It's constantly reinforcing everything that came before it.
okay, before we get to how that security actually works, how does value move? You said it's not like a bank account.
Right, that's a really key point. Bitcoin doesn't have balances and accounts. It tracks something called UTXOS, unspent transaction outputs.
Unspent outputs.
Yeah. So instead of the network knowing you have $10, it just knows there's a $10 output from a past transaction that belongs to you and that you haven't spent yet. It's like a digital envelope with $10 in it.
And if I want to pay someone $3.
You use that $10 UTXO as your input. The transaction then creates two new outputs. One sends $3 to the other person's public key,
And the other,
sends $7 the change right back to a new public key that you control.
that makes a lot of sense. Okay, so we have this chain of blocks linked by hashes, but we still haven't solved the big one. Who decides which block comes next? How do you do this in a distributed way?
That is the absolute genius of the paper. That's the leap.
Yeah.
You need a way to create this order that is so incredibly expensive to fake that it becomes more profitable to just be honest.
And this is where proof of work comes in.
This is proof of work, or POW.
So why do we need work? Why not just have everyone agree on the time and sign the block?
Because that's cheap. Copying data, signing it, that's trivial. Anyone could create 1,000 fake blocks a second and flood the network with fake histories. You need to introduce real-world cost, economic scarcity.
Okay, so how does proof of work create that scarcity?
The system makes nodes, we call them miners, compete. They have to search for a specific number. It's called a nonce. And when you combine this nonce with all the transaction data in the block and run it through a hash function, like SHA-256, the final hash has to meet a really specific, difficult criterion.
Which is?
It has to start with a certain number of 0 bits.
Zeros. Why zeros? That sounds incredibly arbitrary.
It's like a lottery. Because of how cryptographic hashes work, there's no way to predict the output, so the only way to find a hash that starts with, say, 19 zeros is to just guess.
You just keep trying random nonces over and over again.
Over and over, millions of times a second, until you get lucky. And the amount of computing power that takes is absolutely massive. It's exponential.
So it takes a huge amount of work to find the answer.
But it takes almost no work to check it. I can just run one hash and instantly see if you did the work. That's the key. Asymmetric effort.
And that expended CPU effort, that's the security.
That's the seal on the block. Once a miner has done that work, you can't change anything in that block without redoing all of that work, plus all the work for every single block that came after it.
I know a lot of people push back on the energy usage of proof of work. They say it's just waste.
And the paper's argument, implicitly, is that the energy is not waste. It is the cost of security. It's the cost of decentralized consensus. If it were cheap to do, security would be cheap, and anyone could rewrite history. The energy is the price you pay for finality without a third party.
The cost is the feature, not the bug.
It's the economic anchor that makes the math real.
Okay, so that brings us to consensus. If anyone can be a miner, and two people find a valid block at roughly the same time, how does the network agree on which one is the real one?
POW solves that too. It's not one person, one vote. It's one CPU, one vote.
One CPU, one vote.
The rule is simple. Always follow the longest chain. Because the longest chain is, by definition, the one that has the most proof of work, the most computational effort invested in it.
So you don't need to trust anyone. You just trust the chain that was provably the hardest to build.
Exactly. You vote with your CPU power. By choosing to build on top of that chain, you're cementing its lead.
And the system even self-regulates, right? The difficulty of finding that nonce changes.
Yep. It adjusts automatically to target a new block roughly every 10 minutes, no matter how much faster computer hardware gets. It's this beautiful feedback loop.
Well, let's quickly recap the whole process.
It's surprisingly simple when you lay it out. 1, new transactions are broadcast to all the nodes.
2, nodes collect them into a block and start racing to find the proof of work.
3, when a node finds it, it broadcasts the finished block.
And 4, the other nodes only accept it if all the transactions inside are valid and unspent.
Then everyone immediately starts working on the next block, chaining it to the one they just accepted, and the race begins again.
Okay, the economics. All of this computing power, all this electricity, it costs real money. What's the incentive?
The incentive is the key to the whole thing. It comes from 2 places. First, new currency. The very first transaction in every new block is special. It creates a brand new coin out of thin air,
The block reward.
and it gives it to the miner who found that block.
This is that gold miner analogy, isn't it?
Right.
Miners spend resources, CPU time, electricity, to add new gold to circulation.
It's a perfect analogy. That reward is the main incentive and how the coins are distributed in the first place. The second source is just transaction fees.
On the change we talked about earlier.
Exactly. Any little bit left over between the inputs and outputs of a transaction goes to the miner as a fee.
And the block reward isn't static. It gets cut in half periodically.
The halving, it's designed to be deflationary. Eventually, the reward will go away completely, and the network will be sustained only by transaction fees. The system becomes totally inflation-free.
This brings us to the system's ultimate security defense, which is all about self-interest. The attacker's dilemma. What stops a greedy attacker who gets control of, say, 51% of the network from just rewriting history and stealing everything?
Well, the paper argues that it would be more profitable for them to just play by the rules.
How so?
If you have that much computing power and you play honestly, you're going to earn the majority of all the new coins and transaction fees. You'd become incredibly wealthy. But if you use that power to cheat, to double spend and destroy the integrity of the ledger,
You destroy the value of the very coins you're trying to steal.
you invalidate your own wealth. It's a fantastic check and balance. You're economically incentivized, to be honest.
It's brilliant. Okay, a quick word on privacy. Everything is public, right?
The transactions are public, but the identities are not. Privacy is maintained because the public keys are anonymous. You can see that an address sent money to another address, but you don't know who owns them.
And the paper suggests using a new key pair for every single transaction to make it even harder to link them together.
Right. Though, as we said with the UTXO model, if you combine 5 old inputs to make one payment, you do reveal that those 5 addresses were all controlled by the same person, so it's not perfect privacy.
Okay, let's wrap up with the security model. The paper actually uses math to prove how safe the system is.
It does. It frames an attacker trying to build a longer alternate chain as a classic probability puzzle.
The gambler's ruin problem.
Exactly. Imagine the honest network and the attacker are 2 gamblers. Every time a new block is found, it's like a coin flip. If the honest network finds it, they get a +1 lead. If the attacker finds it, their deficit shrinks by 1.
And the question is, what's the chance the attacker can never catch up and overtake the honest chain?
The math shows that as long as the honest nodes have the majority of CPU power, the probability of an attacker catching up drops exponentially with every new block that gets added.
Give us a concrete example.
Okay, say an attacker has a pretty significant 10% of the network's power. After your transaction is in a block, you wait for just one more block to be added on top of it.
One confirmation.
The chance of the attacker ever reversing that is already under 10%. But if you wait for 5 blocks, about an hour, the probability of them succeeding drops to less than 0.1%.
That's incredible. So just a little bit of time gives you this immense computational security.
It really demonstrates the power of the whole system. Consensus is achieved purely through this verifiable economic effort. No trust needed.
So to bring it all home, the ultimate takeaway for you listening to this, what is the fundamental revolutionary power of this document?
I mean, the paper didn't just invent a new kind of database. It invented a system that replaces the need for our traditional institutions of trust, our banks, our legal systems, with something totally new: math and verifiable proof, backed by the hard physical constraints of energy and economics. It was a technological solution to a social problem that's thousands of years old.
The idea that math and energy can enforce rules better than people in courts, that's a profound thought to end on. Thanks for listening to Satoshi and Solana, your guide to making sense of crypto one episode at a time. Subscribe for more insights and stories from the world of blockchain.